Hello everybody, my name is Jerry. Today we present my research on how the augmentation affects what neural network learns. The research was supervised by Dr. Matri, Dr. Cyprus, Sachi, under the Matri Labs. In real life, transformation like corruption, rotation, and corruption happen to the collected data all the time. However, machine learning model doesn't handle them really well because of the lack of transformed sample in the training data sets. As we can see in those images, when we rotate a frog image by 45 degrees, we can fool the model immediately, and it would predict this image a cat. So people come up with this idea called data augmentation, where we try to add augmented images from the original data with a certain kind of transformation. Data augmentation, when we apply in machine learning, is really efficient with a small trade-off in training times. Despite its popularity, our understanding of this technique is still limited. So in this research, we attempt to understand the effect of data augmentation on neural network. We can analyze this effect using the neural network representation. Representation is basically the way you organize data in a compressed form. In neural network, representation is the second to last feature vector. Also, representation had the interesting property of clustering objects from the same class near each other. As we can see in the image, number 1 images is clustering near each other and near number 7. Number 8 is clustered near each other and near number 0. We call a model invariant if the model is able to capture augmentation. So if the model learns invariance, we expect the augmented and the standard representations to be close to each other. We hypothesized two mechanisms that could happen to neural network after data augmentation. Firstly, the model could learn invariance, which it would develop similar representation and prediction rule for standard and augmented model. Or the model could learn a superpopulation of prediction rules for each individual augmented sample. To test our hypothesis, we trained ResNet 18 models on the C410 dataset with two types of augmentation, which is Grayscale and 90-degree rotation. We then obtain prediction and representation of each model to calculate the accuracy, correlation, and the nearest neighbor diagrams. Looking at this accuracy chart, we can observe that the Grayscale testset performed pretty well in the standard model already. However, after testing it again in the augmented model, it doesn't increase the accuracy, but even decrease the accuracies. One explanation for this is now the training data is bigger, so it will be more difficult for the model to generalize the data. However, in the natural rotation test sets, it performed pretty badly in the standard model. However, after data augmentation, it boosts the accuracy to 0.8 accuracy, which is very beneficial for us. So correlation is our next metric to quantifying the performance of the model after data augmentation. The standard model prediction on the standard test set and the array test set is relatively correlated to each other. However, performing the same compilation on the Grayscale model, we achieved a strong correlation of 0.95, which suggests the Grayscale model have learned invariance. We now then shift our focus to the 90 rotation model. Next, the 90 rotation test sets and the standard test sets show near to no correlation at all in the standard model. After data augmentation, it boosts the correlation to near 0.6, but this is still very arbitrary. So we also train a second 90-degree rotation model as a baseline. We then calculate the correlation between the first and the second 90-degree rotation model, both on the standard test set, and we get the similar correlation up near 0.6. So even though data augmentation does with the model correlation, it is still as random as the correlation between two completely different models. So we attempt to solve these issues by training a model with random rotation and test its performance. To train a random rotation model, we transform the sample from a training test set with a random degree from 1 to 90. We then calculate the correlation of the standard model, the random rotation model, and the 90-degree rotation model on the radial rotation test set from 10 to 90 degrees with a step of 10 degrees between each test set. Correlation-wise, the random rotation test set surpass to other model in the test set from 10 to 80 degrees. However, the 90 rotation model still hold the best correlation in the 90 rotation test set. So the introduction of random rotation doesn't improve the augmented correlation at all. In conclusion, our results suggested data augmentation has a range of behavior on deep representation. Depending on the severity of augmentation, model can vary between learning invariance or learning entirely separate augmented subpopulation. So thank you for listening. And if you have any further questions, please contact me using the following email. Thank you.